Better ask a lot of questions. Nico, I need you next to a microphone.
So welcome back. So before we start, actually, please, everyone wear your masks. It is still compulsory inside to wear them, so I see many people not wearing them, so put them back, please. Okay, so great. So now we start with Chris Akers' set of lectures on bulk reconstruction.
Great. Good morning. All right. So in quantum gravity, in the past few decades, there's been a lot of interesting questions that have arisen. Some of them are, how does bulk space-time locality emerge, right? Because in examples like ADS-CFT, the gravitational space-time seems to have one extra dimension of space, so where did that extra dimension emerge from? And do black holes have firewalls? What happens near the singularity? Lots of interesting questions that we want to answer. And I claim that ADS-CFT offers a somewhat direct route to answering these questions. And the algorithm is the following. So with ADS-CFT, what you could do is formulate your question in gravity. So gravity here, that's the bulk. I don't know if everyone's familiar with this language. When I say bulk, I mean the interior of this can of soup that describes ADS-CFT, where the CFT is the boundary. So there's a bulk and there's a boundary. So you formulate your question in the bulk. Is there an audio issue? And then with that question formulated in the bulk, for example, like you can ask, what's happening inside this black hole? That's a question that's easy to formulate in gravity. Then you map it to the boundary using the ADS-CFT dictionary. And then the boundary, it's a CFT, which has no gravity. So in principle, we understand everything there perfectly, even if in practice, some of the computations are too difficult. Right? And then you could answer it in the CFT. Okay, so we have the straightforward algorithm that I claim could answer all these questions we have about gravity. So that leads to a question. Why weren't we done with quantum gravity 25 years ago? Or at least quantum gravity in ADS? Why do we still even study quantum gravity in ADS? So where's the bottleneck? I claim it's not point one. We have lots of good questions. We said some of them earlier. I don't think number one's the bottleneck. There could be more questions, and you as young students, I'm sure will come up with many good questions in your time that no one's thought of. But I don't think this is the bottleneck. It's true, there's something we don't understand about 3, like n equals 4 super Yang-Mills is not a completely solved theory. But I don't think 3 is the only bottleneck here either, because we haven't just all forgotten gravity and decided to study holographic CFTs. Like, we don't all just study CFTs when we're trying to understand gravity, right? There's something else. There's a reason we study ADS-CFT beyond, and when we do that, we don't just study the CFT. That's because there's a huge bottleneck here at step 2. Whenever we formulate a question like, what's happening inside this black hole, it's actually not completely known, or known very well at all, how to map that question to the boundary. So we can't even do step 2. We've learned a lot, so the content of these lectures will be to explain exactly what we know about 2, how we know it, and so on. But there's still a lot of questions to be answered. And so it's this step in this 3-part algorithm for answering all of our questions in quantum gravity that we will talk about. So bulk reconstruction, this is basically to say we want to understand the ADS-CFT dictionary, or the ADS-CFT map. And in particular, this is going to take a very specific form. where we're going to have some operator in the bulk, like say some operator inside of a black hole or something, somewhere in the bulk, and we want to write that as some operator acting in the CFT, and there, then we're at step 3, where we'd have to use that operator in correlation functions or something to get the answer we want. But this is going to be a question of mapping operators in the bulk to operators in the boundary. Okay, so before I tell you some specifics, let me just say there's a number of reconstruction schemes now, and people are coming out with more and more all the time. My focus won't be to review all of these different schemes that people have come up with. It's going to be to make some scheme-independent statements about what can, in principle, be reconstructed and what can't, and how we know that. So there's going to be some theorems. These theorems will be the meat of these lectures, and they're going to tell you what can be reconstructed in principle and what can't, and how you would do it. Okay, good. So now let's begin talking about what we know about the dictionary. So any discussion of the ADS-CFT dictionary has to begin with the extrapolate dictionary. This is something fundamental to ADS-CFT. I think this might have many different names. I forget who exactly called it the extrapolate dictionary first, and you'll see why it is naturally called this. I think this was first explicitly written down, not in Maldaceno's paper or Witten's paper that followed it, but in this paper from '98 by Banks, Douglas, Horowitz, and Martinek. So I'll just write the acronym for now. You can ask me about. So it's Banks, Douglas, Horowitz, and Martinek from '98. So they first start talking about this version of the dictionary. So this is something fundamental about ADS-CFT that comes from the derivation of the duality itself. And this dictionary is an equivalence between certain correlation functions. It says the following. Okay, so it says, consider some correlation function in the bulk. So let's say, for simplicity, we're going to talk about one bulk field. Let's call it phi. So this is some bulk field. And the coordinates I'll use to parameterize where phi is acting will just be x and z. So x will represent most of the coordinates, including the time coordinate. So I'll just say this phi insertion is at x1. And then there's going to be one other coordinate z, which tells you how far from the boundary this phi is being inserted. So if I were to draw, this is a time slice of ADS-CFT, where a CFT time slice is the circle itself, and the ADS time slice fills in the disk. This phi might be acting here, and this is at the point x1, z, where z is 0 at the boundary and then grows as you go in. So these are like the coordinates that I think Brian was using yesterday. So there's this field, and then maybe we want to talk about a correlation function between phi's at different points. Let's say it's an endpoint function. And we're for simplicity, just going to put them all at the same value of z, but their x values can be very different. So maybe the different insertions are here, here, and so on. Okay, so this is some bulk correlation function. And the statement of the extrapolate dictionary is that if you scale this appropriately, so we're going to multiply this by z to the minus n delta. I'll tell you what delta is. It's a constant. N is the number of insertions we have here. And then you're going to take a limit as z goes to 0. So this is like, you're considering a limit of this correlation function where all the phi insertions are going to the boundary. That this quantity equals a certain correlation function in the dual CFT. What is that correlation function? there's some operator O. This is the dual operator to phi. So the statement, right, is that there exists some O such that this is true. So this is some operator in the CFT. It's going to be inserted at the same value of x1, right? So we've gotten rid of z on the left-hand side. All that's left is of this guy is x1. So he shows up there. As a CFT operator, this has an operator dimension delta. That's the delta that shows up here. So this delta is some number associated to this O. Okay. So if I finish writing it, this is some CFT correlation function. And the statement of this is a fundamental statement in ADS CFT. It's this one. These correlation functions match. So in principle, this essentially specifies the duality. Good. But there's a major limitation. Let me write it like this. And the limitation, I claim, is fairly obvious. It's that if we want to compute some correlation function that's like a 4-point function of bulk operators inserted very near the boundary, we're good. We can use the Extrapolate dictionary to do this. But these aren't the only questions we have. These aren't the only correlation functions we want to compute. We might want to compute a 4-point function of insertions deep in the bulk without taking the limit. And here it's not obvious that you can just directly use the Extrapolate dictionary. In fact, it's not just a simple application of this. Right? So you'd like to have something a little bit more than the Extrapolate dictionary. Perhaps derived using it, but something a little more than just the statement. So this need was addressed in 2006 by a paper authored by Hamilton, Cabot, Lipschitz, and Lowe. So Hamilton, Cabot, Lipschitz, and Lowe in 2006. Yes. Who said Chris? Okay. Yeah.
I'm a little confused with what you're saying, because on the left one that you said we can do, I mean, that has no z limit, right?
Okay, yeah. So this was a little heuristic. I mean, this is you can do this with this scale, like with the scaling, right? And so this is telling you about a certain piece of this correlation function, like this leading piece,
right?
And this z expansion. Yeah.
Okay. Thanks.
Yeah. That's a good question. Okay, but you can also, of course, like many things that I'm talking about right now, you can see a great review. So you can read this paper, or you can see a great review by Daniel Harlow from 2018. So this is his TOSI lectures, if you look him up online. So he gives a great overview of what we know about bulk reconstruction prior to 2017. So my focus in these lectures is actually going to be to summarize quite briefly the stuff that happened before 2017, and then actually to go into much more depth about the stuff that happened since then. So currently we're pre-2017. There's a great review here. So there's a new reconstruction scheme that, as I will explain, is basically derived from the Extrapolate dictionary, plus a little bit more machinery. And it goes under the name HKLL reconstruction. So this is important for everyone to know this name because people will often say it. So the idea, I won't go through the details, but the idea is that any bulk operator, but any bulk operator has to solve the equations of motion in the bulk, which is some PDE. And you can solve these equations of motion, using Green's function methods with certain boundary conditions at spatial infinity. And those boundary conditions are given by the Extrapolate dictionary. So the slogan is that you're solving the equations radially. And what happens when you do this is that, at least in certain special cases, you get a very nice closed form answer for how to write, say, some phi on the boundary. So these special cases include, you start with, say, vacuum ADS, and say, let's say, a free scalar field. And then you can write the following form, the following reconstruction. So you have some bulk operator phi, and it can be written as an integral over some patch of the boundary. I'm going to explain what this is. So to tell you ahead of time, it's a set of boundary points, space-like related to this point x. So I'll come back to this. So you're integrating over these boundary points. Boundary points I'll write as capital X. And integrating over this operator at that boundary point. So this is the same operator that shows up in the extrapolate dictionary here, dual to phi. And included in here is some kernel, some Green's function that I'm not going to write out, but it has a known form. It's a known thing. And for talking about operators acted on vacuum ADS for, so let's say a free scalar field, you get this. It's possible to include interactions and perturbations to the geometry, and those are sort of included as extra terms here. They show up that way, but I'm not going to say much about that. Let me just clarify what this S is. Okay, so I'm going to draw the global picture of ADS, which is the can of soup. And you know, some time slice on the boundary might look like this. Maybe we've inserted phi. The phi is acting here in the bulk. We want to write this as some operator on the boundary. So what this is saying is, okay, there's this region S of x, which you find as follows. Consider the past and future light cone of phi. So the past sort of comes out like this, and we're just going to not care about it after it hits the boundary. And then the future, something like this. All right, the drawing gets a little messy there. And all the points on the boundary that are space-like related to phi are the ones in this wedge. So I'm going to try and draw a circle that corresponds to the sort of top cut and the bottom cut. And this integral is an integral over this region of the boundary between these two lines. Is it clear what I'm drawing? Okay. Okay. All right, this is nice. And it actually turns out you can do a little bit better. You don't have to integrate over all of these bulk points. If you want, you can write phi of x as an operator just on a single time slice of the boundary. And the way you do that is you write all of these O's in terms of operators on a single time slice using the CFT equations of motion. So what do I mean? I mean, consider just a general field theory, but in particular, we're going to apply it to the CFT. So this is some time slice in the CFT now. I'm just looking at the boundary. And we have some, let's just say we had some operator here at a later time, O of x at t. Let's say this was t equals 0. I claim that you can write this guy, basically in the Heisenberg picture, you can just write this guy as, so this is his past light cone, use it like in the boundary causal structure. You can write this guy as some operator here. On this time slice, so, with support entirely within the light cone. And the way you do that is you basically, he just looks like this. So you have, yeah, he basically just looks like O of x at this time, but conjugated by the time evolution operator. So how does it work? I think these are the right signs. So it's like, so it's this operator, where this H is the CFT Hamiltonian, and it essentially takes this time slice, and then time evolves forward, and then acts with O, and time evolves back. So that's morally why it works, but it's an operator that is applied here. And it's a very messy operator. So it's not, like this guy was very simple, he was just some local operator here, but down here it'll in general be a very complicated thing. Complicated in the sense of involves many operators that could be very nasty, like a bunch of Wilson loops or something. Okay.
Chris?
Yeah.
Going in the top word, how should I think of K? Like, should I think of it as a boundary to bulk propagator, or?
Good. So it's not the bulk to boundary propagator that you might be thinking of. So there is such a thing.
Like not like a Witten diagram thing.
Exactly. It's not that exact thing. It's slightly different. So that thing I believe is. So this thing is not at all symmetric in the two arguments, x and capital X. I think the bulk to boundary propagator is symmetric. It's not symmetric. No. It's the bulk to bulk that's symmetric. Okay, yeah. So, but yeah, I know these things are not the same. Yeah. Okay, so with this idea, you can basically take this operator written here, and then change all of these O capital X's, which can exist at many different time slices, and then for each one that's not at some time slice you choose, say t equals 0, you just, using this procedure, write it as some complicated set of operators on that time slice. So you really only need, say, one time slice to reconstruct some operator in the bulk. Because that's true, yeah. That's basically how we'll talk about reconstruction from now on, as reconstructing an operator with a time slice, like just on one time slice. Okay, good. So that's HKLL reconstruction. I'm going to say a little bit more about it in a second, but first, I want to ask the following question. The question is this everything we want? It gives us some way of writing bulk operators as boundary operators. Is it good enough? Can we just stop here? And the answer is not really. Because the problem is, it doesn't appear that such Green's function solutions generally exist. For example, for geometries far from vacuum ADS, right? So, the Green's functions that you may be most familiar with involve points separated in time. So you have some boundary condition at some time, and then you're solving for what the solution looks like at a later time. And there's some guarantees about when those exist. The guarantees are much worse when you're talking about space-like Green's functions like this. But the basic problem can be illustrated with this example. Let's say we have the two-sided black hole. So the idea is that this is like the left CFT, this is the right CFT, this is something that Brian mentioned yesterday. This is the future and past singularity. So inside here is inside the interior of the black holes. Okay. And one thing we might want to do is reconstruct some operator here. That would be nice. Could answer some of our questions that way. But if you draw the past and future light cones, they hit the singularity, the future ones. So it's not clear. So in fact, you have this obstruction when you try and solve the equations radially. That in doing so, the singularity, there's some patch of the singularity that's space-like related to your bulk point. So this is essentially the issue. So HKLL doesn't appear to give us nice answers for operators behind a black hole horizon. Okay, so that's the issue. So this is why we didn't just stop here historically. People considered more powerful methods of bulk reconstruction. So, but before I move on to these non-HKLL methods of reconstruction, let me say one more thing about HKLL. That thing is that it's actually not necessary to use the entire boundary. So here, we talked about how you could write this operator as some operator on some time slice, but using the entire time slice. You actually don't need that whole thing. One thing you can do is what's called Rindler Reconstruction. So this is also in these papers by HKLL. And the idea is that it's sufficient to use a subregion. So when you're solving these equations of motion radially, you don't have to actually go in every direction. One thing you can do is basically go in one direction. There's sort of a limit to that, but so let's say you have some bulk operator here. My artistic abilities might limit me in how I'm able to describe this, but the claim is that there's some boundary subregion, say this guy. Let's call him B. Is it clear? So this is a subregion of some boundary time slice, and that you can actually reconstruct phi just on this guy. And yeah, the rules are. Yeah. So when can you do this? When you do this, it'll look very much like this, but this integral will be over some different smaller set of bulk points, and this k will be different. That's the difference. But they showed you can do this, and the rules are that in order to reconstruct phi on B, phi has to be in the causal wedge of B. And the causal wedge is defined by taking this boundary region B, finding its domain of dependence on the boundary. So the domain of dependence is the region of the boundary that is causally completely determined by the information in B. So it's like, it'll look like some diamond. So this is like the future part of the domain of dependence. This is the past part. So you're just drawing the boundary of its past and future. And so given the domain of dependence on the boundary, consider now its bulk causal future and causal past. So if you took every point in this domain of dependence and then you considered its future in the bulk, that would be some light cone coming up this way. If you considered all of their pasts, that would be some light cone coming down like this. And then you have to consider their intersection. So that's some wedge here that's going to have some edge like this. And as long as phi of x is in that wedge, then you can do Rindler reconstruction of phi on B, at least whenever the geometry is sufficiently nice that HKLL works at all. Okay, so yeah, there's two questions, I think.
So does HKLL work always if you use the whole boundary, not the Rindler reconstruction, where in that case I think it works only with causal wedge? But if you use the whole boundary, does it work any time that you don't have an horizon, or are there other cases where it doesn't work?
No, yeah, you should expect that it probably does not work very often at all. So it's known to work near vacuum ADS and perturbations on top of that. As far as I understand, it's not understood if it works much more generally, but if the background geometry is very weird, then if it's something very far from vacuum ADS, then the K you have to use will generally be very different, because very different than the one that works for vacuum ADS, and it's not even clear for geometries without horizons if those always exist. Yeah.
Thank you.
So I just wanted to clarify, I understand. So is this why you drew the first operator inside the black hole? Does Rindler reconstruction ensure that we can reconstruct any operator in the exterior?
Good, yeah, thanks. Okay, good. Thanks for the question. So yeah, the question is basically, let's, in this picture, consider this guy here, this phi. Let's call him phi 2. So if I tried to do global HKLL, global is the name of the one where you use the entire boundary. It would also appear not to work, because you'd have, sure, space like this way, that exists here, But space like this way, you also run into the singularity, so maybe there's an issue there. But in fact, because there's Rindler reconstruction, it suffices to just solve the equations this way. So in fact, using Rindler reconstruction, you could write phi. Well, the idea is that you could write phi on just this boundary, if it works.
Chris,
Yeah.
question. What if I imagine a geometry that's like, so not quite an eternal black hole, more like a wormhole with a throat into extremal surfaces? There would be like I think it's called a causal shadow. What if like the operator is like in the causal shadow? It's neither connected to either boundary, so it would be like it would be a problem.
Yeah,
okay.
Huge problem.
Okay.
Yeah, so HKLL is pretty limited in this regard. Yeah. So that's why, we're going to move past this momentarily. The last thing to say is that this Rindler reconstruction idea is actually quite deep. Later on, I'm going to explain exactly why it's so deep, but the reason is that this is the first incarnation that you're seeing of what's called subregion duality. So this was already mentioned by Jeff. The idea is that you can reconstruct an operator just using a subregion, like in this region of the bulk, just using the subregion B on the boundary. And that actually has huge implications, and we'll get to those. But I'm going to delay talking about it until I introduce the more complete version of subregion duality. Yeah, 2 questions.
So the first question is, in some sense, the diagram on the right is intuitive. We expect this causal reconstruction. The Rindler reconstruction was a bit more
surprising,
involved. But what's the intuition behind that? That we go onto the boundaries and then we consider their bulk light cones and we take the intersection.
Yeah. I don't have a great way of describing it succinctly. Maybe someone else in the audience does. But at the level of differential equations, it works because there's this, the first thing that they did was global HKLO. But then you can notice there's this ambiguity in the Green's function, like many different ones would actually work. And you can consider that ambiguity as, you're free to add a term of a certain form. And this term, you're actually able to use to cancel out part of the support on the boundary. That's sort of a mathematical explanation. I'm sure there's some other physical explanation, maybe involving conformal transformations of the boundary that I don't have at the ready for you.
Okay, thank you.
Yeah. Did you have a question? Okay. If you combine Gauss-Wald with boundary locality, maybe so. I have to think about it. I don't know. Okay. Yeah. Okay. Good. So, given this shortcoming of these 2 methods of reconstruction, so they each have their own shortcomings. Like we have not yet been able to use them to reconstruct operators inside black holes. We would like a reconstruction scheme that works as generally as possible. And it would be great if we could have some sort of guarantee that you couldn't do better. But where's that going to come from? Well, it turns out, to jump to the punchline, the best clue for what you can reconstruct has come from this quantum extremal surface prescription. So I thank Jeff for explaining to y'all very nicely what that is. But so I'm basically going to assume that you're familiar with it at this point. Right. The idea, though, is that you could take some boundary subregion B and then compute its entropy using this quantum extremal surface formula that tells you to find the bulk surface, some gamma, that extremizes the generalized entropy. And if there's multiple such surfaces, then pick the one that is minimal among those. And this formula has the nice feature that it relates the entropy of that bulk subregion bounded by gamma and B to the entropy of B itself. And this was a clue, right? Like the fact that the information in that bulk subregion was somehow related to the information of this boundary subregion. This was a clue that led people to use the quantum extremal surface formula to derive rigorous statements about reconstruction. And so I'm going to actually write down a theorem very shortly that tells you, in a certain context, everything the quantum extremal surface formula has to say about what can be reconstructed. And it's going to be a really good theorem. It's going to tell us, actually, that you can't do better than what it's telling you. Right, because with HKLL, we didn't have such a guarantee. It told us some reconstruction scheme, but it wasn't clear that you, say, couldn't use B to reconstruct more than it said. We will get such a guarantee here. Before I write the theorem, let me tell you about, I need to specialize the discussion to a restricted context. We're later going to generalize away from this restricted context, but historically, the connection between quantum extremal surfaces and bulk reconstruction was understood in this restricted context, so that's where we're going to start, because it's easiest to state the connection there. Okay. Okay. And this restricted context will be, we're going to focus our attention on just a certain subspace of the bulk Hilbert space. We're not going to consider all bulk states at once. We're just going to imagine that the only states we care about in the bulk are a certain limited set of states, some subspace. So I'm going to call it the fixed QES subspace. And by subspace, I mean it's going to be some, I'll call it H sub. It's going to be some subspace of the full bulk Hilbert space. So for example, there's black holes in the bulk Hilbert space. You can have black holes in the bulk. They're not going to be in this subspace we're talking about. So this subspace won't include black hole states. So what I mean is we're focusing our attention on a subspace of ADS in which the position of the quantum extremal surface is approximately the same in every state. Every state in the subspace, that's what I mean. So what subspace am I talking about? Let's just restrict our attention to, let's say we start with vacuum ADS. That's in our subspace. And then states you can get from vacuum ADS by acting some order 1 number of matter operators. Order 1 in G Newton. So you're not allowed to act some like order 1 over G Newton number of operators, just some small order 1 number. So vacuum ADS plus a little bit of excitations on top. And I claim that this is one of these fixed QES subspaces for the following reason. Let's say we have a boundary region B. Say this is B. So here I'm drawing a time slice, and B is this subregion. And let's just say, just in vacuum ADS, just this one state, you can find the quantum extremal surface, and maybe it's this. Okay. Now let's consider other states in this subspace. So those states can be achieved by acting some excitations of the matter fields. So, but not too many of them, just an order 1 number. I claim that the quantum extremal surface in all of these states will be very close to this quantum extremal surface in the vacuum. And the reason is essentially that the quantum extremal surface formula, right? What defines the quantum extremal surface is that it's extremizing and then minimizing the generalized entropy, the area plus S bulk. And the area term, right? So this guy, he minimizes A over 4G plus S of the matter fields. This is huge. It's got this G, which is very small, right? But by assumption here, in this set of bulk states we're considering, S matter is not too large. There's just an order 1 number of excitations, or let's say an order 1 number of qubits floating around. So this guy is just order 1, much smaller than order 1 over G. So it doesn't move the quantum extremal surface very much. At most, sort of like a order G amount, or like a Planck length amount. So very small. So here I'm exaggerating how big the difference is. So all the quantum extremal surfaces are, in all of these states, very close. And we're not going to worry about these small deviations, because we're only going to consider reconstructing operators that are more than just a Planck length away from the quantum extremal surface. Okay.
So just to clarify, in this example, you fixed B first, but this doesn't require fixing the subregion first, right? Like this definition works for any boundary subregion?
Yes, yeah, we're gonna consider, yeah. So we'll consider this subspace first, in which basically for any subregion you pick of the boundary, the QES is fixed. But yeah, let's say that.
Yeah, I was just thinking there are boundary regions you can pick, like 2/4 of the universe, where you're already on like a classical switching point between the boundary regions, and it seems like any perturbation could get it to switch, no matter how
That's
small.
true, yeah. Which, like, yeah, if the areas are different by some order G amount already, then these order 1 excitations could switch them. So I'm just going to not pay attention to those those subregions for now. If you want, by fixed QES subspace, we actually can just talk about a single subregion and just talk about a subspace in which this one guy is fixed.
Okay, sounds good.
Yeah. It won't matter too much for this statement of the theorem. Yeah, we have a question up here.
This fixed QS subspace basically a code subspace, or is there some difference between the two?
That's a great question. So is this a code subspace? So I haven't introduced codes yet, and I will do that. This will be in the first, for now, all code subspaces that I'm considering will be such fixed QES subspaces. Later on, I'm going to consider code subspaces that are bigger, that are not fixed QES subspaces. So I do not take fixed QES subspace to mean code subspace. But for now, in that language, I'm only going to consider code subspaces that are fixed QES subspaces. Okay.
Hi, is this all in one time slice that we're considering the QES, or is it just the entire geometry?
Yeah, so let's just say, you could define such a subspace for the entire geometry, and that would be a more restrictive thing. But yeah, for now, for simplicity, to go back to a question asked earlier, we can just imagine we've picked a boundary region B, and then we're considering like some time slice in which its quantum extremal surface is minimal, and we're just talking about this QES and fixing this. We would just want this QES to be the same for all states in the subspace in this time slice, or any time slice. Does that make sense?
So we are fixing B first.
Yes, let's fix B first. Okay. It won't really matter, but that'll be simpler. Yeah. Thank you. Okay. Good. So it's in this context that a very amazing theorem holds. And this amazing theorem was written in this form I'm going to show you first in Harlow 2016. So he's a single author paper from 2016. There were some important parts of this theorem proven in earlier papers. For example, there's a paper by Dong, Harlow, and Wall earlier that year that proved a part of this theorem. And this all depended on earlier papers by Jaffrus, Lukowitz, and Maldacena and Suh from 2015. And then also, part of this theorem was proven in a very limited toy model in this very readable paper from 2015 by Harlow, Postowski, Preskal, and Yoshida. But in this form, it was in this paper. And before I write the theorem, so this is what we're going to call Theorem 1. Let me tell you some caveat, or like a little cheat that I'm going to make. For simplicity, I'm going to write everything in terms of a finite dimensional Hilbert spaces, which to apply that to ADS CFT, you would need to regulate the field theories on both sides. That's okay. Or if you really want to be serious about it, one thing you can do is ask if there's a version of this theorem that is not worded in terms of finite dimensional Hilbert spaces, but it instead talks about infinite von Neumann algebras. And such theorems have been found. So there's this impressive work by people like Tom Faulkner, Monica Kang, and David Kolchmeyer, and other people that has generalized the theorem that I'm about to write to infinite von Neumann algebras. That would be much harder to tell you. So I'm going to stick with this much easier to digest finite dimensional Hilbert space form. And from now on in these lectures, I'm only going to talk about finite dimensional Hilbert spaces. But you can keep in the back of your mind that these theorems, we do expect them to apply to ADS-CFT, perhaps by introducing a cutoff there, or generalizing the theorem to infinite von Neumann algebras. Okay. So, good. With that caveat aside, let me write the theorem. So, we're going to have two Hilbert spaces. The first one is going to be what I'll call H, or H phys maybe. You'll see why. So this is like H physical. And it's going to be a tensor product between two systems, H capital B and H capital B bar. So this you should morally think of as like the CFT. This is like the CFT Hilbert space, where B is some boundary subregion we're considering, and then B bar is its complement on the boundary. Okay, in addition to this Hilbert space, there's another Hilbert space, which we'll call H code. I haven't explained why I'm calling it H code. We will explain that later. But for now, just know this is a historical way of talking about this. And this will also tensor factorize. So it'll be like H little b tensor H little b bar. And you should think of this morally as the Hilbert space of the bulk. And little b is the region that is inside the quantum, like between the quantum extremal surface and capital B. And then little b bar is the complementary bulk region. Okay, so there's these two. They're finite dimensional Hilbert spaces. And in fact, this is not just the bulk, so let me just emphasize again. So this is a fixed, this Hilbert space is a fixed QES subspace of the bulk Hilbert space. So this little b is defined, right? So it's the region of the bulk that is always bounded by quantum extremal surface and capital B. Yeah.
Do you expect, or maybe this is known or whatever, but is bulk non-locality a problem in this factorization of the bulk Hilbert space?
It's yeah, you can deal with that. So I'm going to sweep like details of dressing under the rug, for example. You can deal with that. So for example, if we're talking about an operator in little b, you could imagine that it includes dressing that is entirely contained within little b. And then everything I say will go through because this entire operator is in little b. I won't say much about it because it actually does not change the discussion at all. So.
And is that in part because we're in the fixed QES subspace, or do you expect it to hold in the full bulk Hilbert space?
Good. Yeah, morally it will hold in the full story. That's the answer. Yeah.
Okay, thanks.
Yeah. Thanks. Yeah.
Just a quick question. You can defer to later if you want. When it comes, are there versions of these theorems that apply for, like lattice gauge theories where strict factorization that you wrote down doesn't apply?
Yes, thank you. Yes, there are. I'm not right. So
we can talk later. Just that yes, they exist.
Yes, they exist, and this is actually in this same paper. He proves the theorem I'm about to write, and then generalizes it to exactly that sort of case. So yeah. But for simplicity, I'm avoiding talking about it. Happy to talk about that more. Okay, and then in addition to these two things, there's one more ingredient we need, which is there's this, I'm running out of space. Maybe I'll write it here. So there's this V, which is some isometry. So it's some linear operator that maps states in H code to states in H physical. And you should imagine that V, it's just a tool here for telling you, okay, we're going to have some bulk state, say like the vacuum state, and V tells you what the boundary dual is, which is like the vacuum and the boundary. Okay, so V just maps each bulk state to its boundary dual. Okay, so given this, the following two statements are equivalent. So there's two, and let me actually start with the second one. Why did I write it this way, you might ask? Well, I might have an answer. So the statement is that for all states rho, so rho is a density matrix here, on H code. So for all states of the bulk, the following formula holds. That if you were to consider, I might be writing too small, but if you were to consider the state that you get by mapping rho to the boundary, so here this is V rho V dagger. So that this is just a way of writing the boundary dual of rho. Right? So you just take rho and you map it to the boundary version of itself. Then you compute the entropy of B, capital B, right? So this is the sort of thing you do in ADS-CFT when you're applying the quantum extremal surface formula. You have some bulk state, some boundary state, and you want to find the entropy of some subregion in that boundary state. That's what we're computing here. The statement is that this equals the entropy of region little b in the state rho plus, so far so good. So the quantum extremal surface formula looks something like this, right? Where the entropy of your boundary subregion equals the sum of two terms, one of which is the entropy of the bulk fields in this region. And the other one is the area of the quantum extremal surface. So here, in this theorem, the way we're going to write it is I'm just going to say plus A. And you should have in mind that when you apply this theorem to ADS-CFT, this A is like area over 4G of the RT surface, or the quantum extremal surface formula. Okay. So at the level of this theorem, we haven't introduced any sort of geometry anywhere. So what could this A be? I'm going to explain that in a little bit when we go through the proof. But basically what you need to know about it is it's state independent. Like it's not something that it's like a state independent area. All right, it's not something that depends on rho. This is what you would expect from the area, right? Like it's the area of this surface. Doesn't matter if you put some excitation over here, as long as it didn't backreact on this guy. This guy is, the surface by assumption was the same for all bulk states, so it's a state independent area. Okay. And likewise, there's a similar statement for B bar. So if I replaced these B's with B bars. Okay, and then the first statement, so this is the one that's actually really interesting because the point of this theorem is to tell us what the quantum extremal surface formula has to do with reconstruction. So far, I've introduced this setup, said, okay, these two things are equivalent. One of them is the quantum extremal surface formula. The first one is going to be a reconstruction statement. So it's going to be what we want. And it says that for all bulk operators, so let's call them phi b and like maybe phi prime acting on b bar. So this is some operator acting on little b. There exists some, so I'm putting a prime here so that you know like this is a different operator from this phi. Okay, so there exists some operator on capital B, or respectively some operator on capital B bar. So I'm going to put a prime on this O to tell you that like this one corresponds to this guy, and this OR operator corresponds to this guy. Okay, so for any bulk operators, there exist these boundary operators such that for all bulk states you could consider, so for all psi in H code, I apologize for all these quantifiers I'm writing, like for all and there exists. I know some people's eyes roll into the back of their head when they see these things, but it definitely makes it shorter to write. Okay, so far the statement is, for any bulk operator, you can find a boundary operator that on all states does the job. So the statement is, okay, let me write it one piece at a time. So the statement is, if you had this bulk state, any bulk state in the subspace, and you acted your operator on it, phi b, and then you looked at the boundary version of that, you could have equivalently gotten the same state by starting with psi, first mapping it to the boundary, then acting some operator just on B. Okay, so this is a very important statement. So the statement is that, like this is a reconstruction statement. It says, right, so for any bulk operator you have, there's some boundary operator on capital B that does the same job. Okay, and there's an equivalent statement for it's actually important that it shows up here. So there's an equivalent statement for the barred versions. So if you replaced little b with little b bar, capital B with capital B bar, that would be also true. And also the daggered versions. So like phi dagger is reconstructed by O dagger. So that's also true. Okay. So to make this strictly true, I need to write the same thing for the barred version, and also down here.
Sorry, Chris, a question.
Yeah.
So this theorem says that if one is true, the other one is true, but it doesn't prove that any of the two is true in some specific. So the idea is you use the derivation of one of the two statements to prove that the other one is right?
That's exactly right, yeah. Yeah, exactly. So let me repeat what you said, because I think it was a really good point. This theorem just says they're both either true or both false. And the idea is that, in ADS-CFT, we can derive the quantum extremal surface formula. And so this theorem tells us, therefore, we have this, at least in this context of fixed QES subspaces. So that's the power. It's telling us, exactly what the quantum extremal surface formula says about reconstruction. Okay. Yeah, question?
So this is saying that we can reconstruct with boundary operators on a smaller part of the boundary than the, what was it called, like Rindler wedge type thing? Or
Yeah, that's a good question. Okay, so Nico's question is the following. So, we saw here that we could already do something like reconstruct this, like operators in a certain patch of the bulk, like this patch here, using just a subregion of the boundary. This seems morally similar. We're reconstructing operators in a patch, little b, using just a subregion, capital B. Are those related? So the answer is that this is a more powerful statement. This, in general, is telling you something more than you could do with Rindler reconstruction. So to be precise about it, the region that worked for Rindler reconstruction was the causal wedge of B. So there was this procedure for finding the causal wedge, and it had some definite extent in the bulk. The region that according to this theorem, capital B can reconstruct is the region inside the quantum extremal surface. That's the so-called entanglement wedge. I might slip into that terminology. So that's the entanglement wedge. And you can prove, under very mild assumptions, ones that we believe are true, that the entanglement wedge is always outside the causal wedge. So the entanglement wedge is always bigger. It contains the causal wedge. So this is more powerful because it says you can do more than this told you. Sometimes they're equal, but in general, they're either equal or the entanglement wedge is bigger.
So my question is there like some sort of proof or rough argument of why we could maybe not do better even on the entanglement wedge?
Thank you, yeah. So how do we know that we couldn't improve? This theorem tells you that. So this theorem tells you that, it's because these are equivalent that it tells you that. So it says, let's assume that there was a larger region of the bulk that you could reconstruct, then that would be in the entanglement wedge. So because 1 implies 2, yeah, but if you could reconstruct it, then that region would have to be in the entanglement wedge. So this theorem is telling you what you can reconstruct on just capital B, again in this special context of fixed QES subspaces, is its entanglement wedge and no more. Can't do better. So that's awesome. A nice guarantee. So this is one reason why we all like what the QES prescription has to tell us about bulk reconstruction, and we think that it might be telling us basically everything, at least everything so far that you might want to know. Yeah.
Cool, thanks.
Yeah.
Chris, so connecting to what Nico said, so I guess going back to my example before, this solves that because if you have this wormhole with a causal shadow, you would never be able to reconstruct any operator living in the causal shadow.
Yeah.
But the QES or HRT surface, whatever, always lives in the causal shadow. So somehow there's always going to be
That's right. Yeah. Exactly. So this reaches in further. Okay. So it solves this problem. So in these black hole examples, ideally you'd be able to. Yeah. You can find some boundary region whose entanglement wedge includes that operator, and perhaps you can therefore reconstruct.
And then second question is that A that you get from the theorem, does it have, how do you know its area? Is it is an assumption, or does it satisfy properties of areas?
Yeah.
Or okay.
Good. Yeah. It satisfies many properties of areas. So for one thing, it's this it's a state-independent quantity, as it should be if the quantum extremal surface is not state-dependent in this subspace. Also, it's something that is, measurable on both capital B and its complement. So, in principle, both capital B and its complement, I don't know what I'm gesturing to, should know about the area of gamma, because that's on the edge of what you would expect it would know. In the algebraic version of the theorem that Kristen was alluding to, the statement is that this area is given by some operator that's in the center of the algebra. Yes, those are the basic reasons why it makes sense.
Excuse me. So my question is that what are the properties of the safety on the boundary are we assuming for this setup? So are we assuming that there is this large central charge of the 3-point function as a special structure? Or are we just assuming that there exists a V, and if a V exists, that does this mapping, everything holds?
Yeah, that one. So So in the context of this theorem, right, we haven't said anything about holographic CFTs or anything. So this is just a true theorem, very generally. And then you can take a special context like a holographic CFT and ask if one of these is true, and it's in that context that Jeff proved for you that this sort of formula holds, and that's why we believe that number 1 also holds. Yeah.
So, sorry. So just on this answer, so as we are not using any property of the CFT or any structure of that, we are just assuming that this V exists. So other than ADS CFT, if hypothetically, if there is some other kind of holographic duality, does this theorem hold for that also?
Absolutely, yeah. This theorem is completely, the assumptions are stated here. I haven't hidden any assumptions, so we have this fixed QES subspace, these Hilbert spaces, and a map that relates, this isometric map that relates them.
And it also has nothing to do with the boundary has to be codimension 1? Or
That's right. It has nothing to do with the boundary being codimension 1. Yeah.
Thank you very much.
Yeah.
Sorry, I have 2 questions. The first, so I'm here.
Okay, yeah.
No problem. I guess I didn't understand one thing. In the Rindler reconstruction, are you asking for the field to be in the same time slice as the boundary region or not?
So back here at Rindler reconstruction?
Yes.
So it doesn't have to be, so.
It just has to be in the.
Yeah, so it has to be in the causal development of the.
Okay. Yeah. So I guess, well, this is just because I probably don't know this, but or some other restrictive things or not, that you're not asking in the reconstruction, like, well, I is to have that factorization of your bulk region,
yeah.
and like having this fixed QES space, subspace.
So, yeah, so this is an approximation, like this is sort of a toy model of what happens in gravity, and more general versions, we don't expect that the bulk semi-classical gravity theory admit such a clean factorization, but this was the easiest theorem to present to y'all. There are generalizations, including already in this paper, where it doesn't exactly factorize. It's more general than that. So that's not an obstruction to this theorem morally holding. Your other question was how restrictive is it to have this fixed QES subspace? So we can consider, there are subspaces that we can restrict our attention to that fully satisfy this, like vacuum ADS plus some perturbations on top of that. That's not going to get everything we want, and this is going to be one of the major points next lecture, is what happens if we want to consider, say, a black hole that doesn't fit into such a subspace. But I'm going to delay talking about that until then.
Okay, just because in the Rindler reconstruction you don't have that, right? Well, it's less general, but you don't have that restriction, right?
Yeah, thanks. Yeah, thanks for the question. So I would say that it's not explicit in the Rindler reconstruction, but is implicit, because Rindler reconstruction relied on there being this Green's function that exists that does it, and the Green's function depends on the background geometry you start with, so it works for sort of perturbations on top of that. So it was implicitly there.
Okay,
Yeah.
I see.
Yeah. Okay. There's a question behind you.
For the Rindler case, you had the explicit construction using the kernels. In cases when the entanglement wedge is larger, do you have something like that?
Good. So next lecture, I'm going to talk about some explicit schemes very briefly for how you actually. Right, good. So this theorem, as you're alluding to, is not constructive. It just tells us that that there exists these O's. Doesn't tell us what they are. There are very nice, powerful methods for writing down a reconstruction from quantum information theory, something called the PET, that basically works, if anything, given, yeah.
But in terms of bulk Green's function, does something like that?
Okay, no, so yeah, that won't have this nice form of like a Green's function. It'll in general be messier, yeah.
Yeah, so I have like 2 questions. Maybe this is related to what, okay, hi. Okay, so like my first question is just a clarification. Like V here, does that depend on H code?
In the Rindler reconstruction, is that what you said?
No, in the theorem.
Yes, it depends on H code. And we're going to see this more explicitly later on, but like exactly how it depends. But the answer is yes. This O that you find in general depends on H code. If you chose a different subspace in the bulk and tried to consider the same, say like free scalar field operator, it will be the case that this O would be different in general from this subspace.
Okay, yeah, and my second question, I guess, was maybe related to what's just asked. Like, so can you say anything about like the efficiency of reconstruction procedures?
Oh, like how easy, like how complex it is, or
yeah.
That's a great question, and I'm not going to talk too much about that in this lecture series. But the idea, yeah, so that is something that has recently been of major interest. It's related to, yeah. So the idea is that we think that some operators are easy to reconstruct, like those in the causal wedge. But we don't think that, in general, all operators in the entanglement wedge are easy. In general, it could be very hard to find some, like, the operator that you act on capital B could be very complicated. For some, even simple operators on little b. And this connects to some work that Brian mentioned that Jeff has been a part of called Python's Lunches. And yeah, we can talk about this afterwards, but I'm not going to talk too much about that now. I'm just going to talk about what's possible and what's not how hard. Yeah. Great. These are great questions. So my goal now for the rest of the is to start the proof of this. Because I think it's important to see how these sorts of ideas get proven, because there's a lot to be done, and I would love some of you students to get interested in these tools, learn what they are, and then maybe push the boundaries of what we know. And so I'm going to start the proof and finish it next time. The proof I'm going to show you is not the proof that that Daniel gave in his paper in 2016. It's a different proof. The reason I'm going to give you a different proof is mostly because this version will generalize very nicely to the other theorems we're going to see later. So it generalizes beyond just this theorem, which assumes the fixed QES subspace. And then another nice perk of giving you a different theorem is that you can always go read Daniel's theorems. So this gives you a second way of thinking about it. This is by far going to be the most technical part of the entire lecture series. I think that I hope I'm going to go slow enough that it won't seem overwhelming or anything, but it is certainly going to be the most technical part. And yeah, I strongly encourage you to ask me even the simplest clarification questions. So so to prove this theorem, we're essentially just going to prove that statement 1 implies statement 2, and then that statement 2 implies statement 1. Before I do either of those things, I have to introduce to you one main technical tool that's going to be used in both of them. So it's the real workhorse, or the main tool of this entire proof. And I think along the way, you'll learn some cool quantum information facts. So the main tool. So I'm going to talk a lot about qubits. It's not necessary for the proof, but it'll make our life easier when just talking about it on this blackboard. So for example, I'm going to imagine that little b and little b bar are made up of a bunch of qubits. Okay, the proof does not depend on that, but it's going to be a lot easier to just say things like that. And so the main tool, to tell you what it is, let me imagine that I have two qubits for now, qubit x and qubit y. And let's say qubit x is in some state psi, and qubit y is in some state phi. There exists some operator acting on both of them. Let's call it SXY. That just swaps them. So S is for swap. So now it puts x in the state phi and y in the state psi. And in fact, I can tell you explicitly what this operator is, and I'll leave it as an exercise to you to confirm it does this. So this operator is 1/2 times the sum over I equals 0 to 3 of polymatrix I acting on x. So polymatrix 0, let's call that the identity. Polymatrix 1, let's say it's poly x, and so on. So poly 2 is poly y, So it's identity XYZ. That's what we're summing over. And then we have the same poly operator acting on Y. So I leave it as an exercise to you to confirm that this X, this S, does this. It swaps them. And I'm going to consider a swap acting on all of B and swapping it with an identical copy of B. So when I write little b, I really mean the little b that appears in this theorem, right? So it's some system that, for simplicity, we're thinking of as made of a bunch of qubits. And I'm going to introduce this system little a. Okay, little a is just an identical copy of B. And so B has a bunch of qubits. A has a bunch of qubits as well, the same number. And then this S that swaps A and B is just going to be the product over, I don't know, J. J's, so product over all the qubits of just swapping qubit J and A and qubit J and B, right? So like B had this many qubits and A has the same number, and then this operator just swaps the state of all of them. All right, easy peasy. Okay. So given this swap, that would swap like B with some identical copy of itself, let me define this operator for you. And then I'll explain in more detail what it does. So I'm going to call it WB. It's going to be an operator that acts on little b. And it's defined by introducing some maximally entangled state between two new copies of B, right? So here I talked about, okay, I just brought in an extra copy of B for no reason. I haven't explained it to you yet. I'm going to do that with the second copy. So now we have two extra copies of B floating around. One's called little a, like before. One's called little r. And they're in a maximally entangled state. So I'm going to, over here, draw some pictures. So these will be the pictorial versions of the equations I'm writing. So the idea is actually, let me draw the pictures in a second. So I'll write it in equations, and then we'll talk about pictures. So you introduce this max, right? So max is like, some sum over, I'm running out of indices. Let me just say k from like 1 to the dimension of B. And then 1 over, okay, and then it's just maximally entangled between A and R. And then, of course, normalized. So you have to divide by square root of the dimension of B, because they both have dimension B. That's what max is. Okay, and then act the swap operator SAB. Okay, so I claim that this is an operator on B, and moreover, I claim that it does the following thing. So, and I'll draw pictures, which I think will make it clearer. So let's say you had any state psi. This is a state on like B, little b bar. And so it's like, some bulk state psi. And then we act this operator WB on it. What it does is it just gives you this state. So it's psi on now little a, little b bar. And then max on little b, little r. Okay. So this is the equation. So the main tool is this W guy who does this. And to give you pictures that I hope will make it a little clearer, what is WB doing? Well, we start with some state, some bulk state, right? So you have like little b and little b bar. They're regions of the bulk. And what does WB do when it's acting on this? Well, the first thing it does is it brings in this extra 2 copies of little b. So this hasn't been touched yet. And now we have, I'm going to draw just like, right? So this is supposed to be a copy of this, which we're calling A. And then this is supposed to also be a copy of little b, which we're calling R. and they're maximally entangled, so these lines are entanglement. Lisa? Yeah, AJ and BJ. Yeah, sorry. These are, J is all the qubits in B. So I was just imagining that B has a bunch of qubits, like B1, B2, B3, and so on, and then J is indexing those qubits. Thanks for the clarification question. Okay, so, and then WB first introduces this maximally entangled system, and then it swaps little b and little a. So I would draw it this way. So we end up with a state that's like, you still have little b bar, and then now you have little a here. So, right, so this was in state psi, this is still in state psi, and this was in max. And then now we have these two guys in state psi, and so here this is now little b, and this is still little r. They're maximally entangled. Okay, so W little b is some isometry that acts on little b. So it just sort of does this weird thing. And you could say, why do we care about this? You'll see in the proofs next time that this guy is extremely useful. This is what he does. I'll say it again. Next time I'll write this equation. But yeah, this is the main tool. So that's it for today. Thanks.
Great, thank you. Are there more questions? I guess no, so we will have more tomorrow. Thank you.